Well, hello, Earth Space Science class. We're going to do a plutons and volcanoes video lecture here. I started these notes in class a week ago. And if you remember, we just started talking about igneous rocks and rocks that are formed from magma that has cooled. And we talked about what were the main, well, we talked about lava being magma that's reached the surface, magma being liquid and solid rock. And then we also went on to talk about other things that are found in lava that are important to understanding the behavior of a volcano that might emit that kind of lava. And among those were volatiles, which are mainly water and carbon dioxide. And then I stuffed some dry ice in that little capillary tube, or little centrifuge tube, and put it in that beaker of warm water. And we talked about what happened inside the tube, and it blew up eventually, if you remember, as the molecules of CO2 heated up and wanted to disperse, become a gas, and take up more volume. The tube restricted that until it could no longer restrain it, and it went boom. Kind of left off there, and going with the analogy that that's what's going on inside volcanoes to varying degrees to make some of them explosive, like the one I played you a video clip of, and others less explosive, like a good example would be Hawaii or Kilauea on the big island of Hawaii erupting right now. Silica is also another important point, factor that needs to be considered in figuring out the behavior of magma which might come out of a volcano. Silica makes magma thicker, and that means it's not going to flow as fast, neither up the vent of a volcano nor down the sides of said volcano. So the amount of volatiles and the amount of silica that are in magma are really of chief concern when it comes to evaluating the behavior of a volcano. What we're going to do now is look at sort of volcanoes, and we're going to consider what comes out of them. We're going to say that some volcanoes emit basaltic magma and some volcanoes emit granitic magma. Now, these are either ends of a spectrum, and you need to realize that any volcano could be at either end or somewhere in between. And some volcanoes even change behavior. I'll show you an example of one of those here in a minute. So we're going to start with the hot magma. It's hot, 900 to 1400 degrees Celsius. If you jump ahead, you can see granitic magma is only 600 to 900 degrees Celsius. Another important difference is that the amount of silica that we find in basaltic magma is about 50%. Jump ahead again to granitic magma, you'll see it's up to 60 to 70%. So more silica, which means the granitic magma is cooler, and it's going to move slower, be more resistant to flow, if you will. It'll flow more like oatmeal, whereas basaltic magma will flow more like coffee. And then maybe, most importantly, the last thing is that basaltic magma has typically less than 5% volatiles, while granitic magma can have up to 15%, maybe even more than that, volatiles making up the magma. And volatiles are the gunpowder that are in the magma. They're the charge that determines will the volcano go pop or will it go boom. So we're going to start with basaltic magma. And we're going to look at a few products of it. Now, basaltic magma, you can make the case that most of it occurs under the ocean at divergent plate boundaries, at the mid-ocean ridge, where plates are separating, hot magma comes up to the surface, hits ocean water, and cools. If we look at those products, as I say, most of them under the ocean, but some of them above the ocean, you'll see that there are different types, and one is in the picture right here. This is Pahoehoe lava. Now, Pahoehoe lava is formed from slower moving lava. It gives it a chance to form a hard skin over the surface, and sometimes because it's still flowing underneath, you get these twisted ropey shapes to it. Lava is typically formed in fast-flowing, high-volume lava flows, and here you'll have chunks of crust like this stuff here that breaks into pieces and falls into the lava underneath it, and then more lava coalesces around that piece, and you get these chunks or blocks of lava. And again, this is typical of high volume, fast flowing lavas. Lava's coming down a steeper slope, for instance. Now, those are two characteristic products. Another is if you have a lava that is particularly thin, non-viscous, like coffee. It can spread out over a big area, and whereas lavas that are thicker can form, so your classic volcanoes, like this picture of Mount St. Helens, lava that's thinner tends to flow over the surface and end up flowing almost horizontally, making flows that are almost horizontal. This is not the Grand Canyon. These are flows of lava. You can see one here, another here, another here, another here. This is in Washington State. And these are the Columbia River flood basalts. So here's Washington State, and this is the part of the state that has these in them. There have been some other real significant flood basalts through history. This is the Siberian traps. Traps is a Swedish word, means stair steps or steps. And you can see, again, these layers of lava flows, one after another. But look at how big of an area the Siberian traps flowed over. So this is a huge part of Siberia that has these basaltic flows on it. And then again, we go to India and we can see what are called the Deccan traps. And again, layer after layer of lava flow, and this is the area of India that had them. Now I'm going to back up here for just a second. I want you to notice something here. The Siberian traps, that flow occurred about 250 million years ago, MYA, million years ago. The Deccan traps were about 66 million years ago, 66, 65, somewhere in there. If we go to mass extinctions, we can see that, oh, look at that. Here is 250 million years ago. Here is 66 million years ago. It's not a stretch to associate those big lava flows with cataclysmic results on Earth. It's not just lava flowing out on the surface, folks. That lava is going to be associated with gases, particularly sulfur-containing gases. Yeah, CO2 will come out. We all know about CO2 and the greenhouse effect. But far more importantly are the sulfur gases that come out of a volcano that work in the opposite way that CO2 does. Sulfur gases block the sun, block solar radiation, and reflect it back into space. They cause basically a volcanic winter. And we know that in a number of cases, here are two chief ones, that it's believed that those volcanic emissions may well have caused massive extinctions. You can see the percentage. Some say that this is Permian over 50% of everything on Earth. Some have that up in the 90s. Big problem. Now, yeah, the Cretaceous. Some say it was a meteorite slamming into the Yucatan Peninsula of Mexico. May have been involved. May have been both. May have been one or the other that caused this extinction. Don't know, but there's a good likelihood that whatever made that look in India and that look in Siberia affected the whole world. And so, while we talked about earthquakes and how devastating they can be regionally, you might make the case that volcanoes can have an even bigger effect given the gases that they can emit. Well, I'm going to click out of these, and we're going to look at another characteristic feature of basaltic lava. The kind of volcano that would result from basaltic lava would be something called a shield volcano. I'll go to Google Earth here, and the best example I know of is of the Big Island of Hawaii. And so this whole feature here is a shield volcano. And if we look at it, it's dominated by one particular volcano. This is Mauna Loa, and you can see flows here going all the way down to Hilo, all the way over here, all the way over here. So this whole part of the island is dominated by that one volcano, Mauna Loa. Kilauea is over here on the flanks of Mauna Loa. But this one is large. In fact, if you took all the other Hawaiian islands and lumped them together, they wouldn't be as large as that one volcano. So if you look at it in cross-section, so here's a real shot of Mauna Loa. You can see the very gently sloping sides. And if I go back to Google Earth here to give you an idea for how many miles are encompassed here, we'll just go across, not even the widest part, we'll just go from this coast across to Hilo, and that's almost 60 miles. That's one volcano, ladies and gentlemen. So they're capable of incredible size. If we look at Mauna Loa in the island of Hawaii in cross-section, that's what we've got right here. Yes, indeed, Mauna Loa is the highest, not the highest, the tallest mountain on Earth. The highest mountain is Mount Everest, but Mauna Loa, from base to summit, is several thousand feet taller than even 29,000 foot Mount Everest. But look at the very gently sloping sides, and that's characteristic of a shield volcano. If you get layer after layer of solid lava, very stable feature and massive feature. Here's those layers after layer after layer of solid lava coming out and making a very stable volcano. A lot of concern about Mauna Loa. We hear about Kilauea, which has erupted your whole life. Mauna Loa is way overdue for eruption, and when it does, the concern is that it would send lava down to Hilo, which it has done in the past. You can see these are lava flows. We'll see. Another thing that feature that basaltic magma can produce, oops, that's the one I want, is columnar joints. This is the Devil's Tower in eastern Wyoming, just west of the Black Hills, and these are columns of magma. And the Cheyenne had an interesting idea of how it formed. Believe it or not, geologists today think this is not a volcanic remnant. There's disagreement over what it is, but they say this is not the remnant of a volcano. You know, there's certainly the remnant of cooled magma, and we find it other places. This is the Giant's Causeway in Ireland. Some of you may have been there. Sure looks like extraterrestrials have laid down patio stones here. But no, this is cooled basaltic magma. And here's another Devil's Postpile in California. Why the devil gets credit for this stuff. Here's how this formed. So we'll go back to Giant's Causeway. If you could picture this being molten magma at some point in history, none of these joints, these cracks between rocks were there. As it cooled, as it flowed on the surface and cooled, this whole surface did not cool uniformly. Rather, there were these centers of cooling. It would be the center of each of these polygons. You got to ignore these lines between them. They would not have been there initially. But there was a center here, a center here, a center here, a center here, and here, if you can follow that with the cursor. So as this whole mass of magma cooled, those areas cooled a little more rapidly. Well, if you think about what happens to the volume of a substance that cools, it shrinks as the atoms become more closely packed together, the opposite of what went on in that little tube that we blew up. So as it cools, things shrink. So there's a cooling center here and a cooling center here, and the lava is cooling and shrinking and contracting towards that cooling center and toward that cooling center. Well, a crack would develop right perpendicular between those two cooling centers as the cooling lava contracted towards them. The same between these two, here, between these, and pretty soon you have these polygons, 4 to 7-sided polygons that form as magma cools and contracts towards those cooling centers. And it makes these polygons that you see in the picture. Now, glaciation probably, or maybe wave action, polished them off, but they were originally created as magma cooled and contracted. The last item in under basaltic magma is pillow lavas. And there's a video that I would like you to go look at. It's on your Moodle page right here at the Mid-Atlantic Ridge. You only got to look at the first 22 seconds or so if you'd like. And that will show you a good example of pillow lava coming to the surface at the Mid-Atlantic Ridge under an ocean, so flash cooling. And this would have very small crystals then, pillow lava, because it doesn't have time to form large crystals because of that rapid cooling. Okay, so then we're going to go to granitic magma. And for granitic magma, I want you to look at a couple of clips. These are of the Mount St. Helens eruption. Now, here's Mount St. Helens pre-eruption. This is what it looked like before 1980, May of 1980. And this is what it looked like after May of 1980. It lost over 1,200 feet of its summit. And I suspect you have seen those stills, but maybe you haven't. It's been long enough that this event is falling from our our memory. And so you go here, look at 1 and 2. They're like 2 or 3 minutes apiece, so they're not long. But at the end of 1, you're going to see what we call an ash flow. You look at that's number 2 on the notes list of products from a granitic eruption. Pyroclastic debris is number 1. Anything shot out of a volcano, and I'll have some ash from Mount St. Helens in class on Tuesday for you to look at and touch and feel and all that. But an ash flow is a particularly devastating thing. I always ask my class if Mount Fuji erupted. This is Mount Fuji, and it's towering over the biggest city in the world. That's Tokyo. And there's anywhere between 25 and 35 million people, depending on how you count it, living at the foot of Mount Fuji. If it erupted, what would be a problem for people living in Tokyo? And of course, people say lava. Well, yeah, but really, Fuji probably would not emit much liquid lava. There's 2 things. Number 1 is an ash flow. And so as Fuji erupted, there would be this eruption column coming out of the top of Fuji. And the eruption would continue, maybe get more and more energetic for a while, but after a while, its ability to sustain that level of energy emission would decline. And so part or all of that eruption column would topple over and fall down the side of Mount Fuji and slam into the western portions of Tokyo. Now that ash cloud would contain very abrasive material, fragmented rocks, particles of ash, noxious gases, droplets of lava. Nothing standing in its way would survive. And so that would be one thing that would be a real problem for Tokyo. And at the end of video 1, you'll see a clip of an ash flow coming out of camera, and it's a scary thing. Then also, this snow and ice would melt almost instantaneously. And then you would have water perched on the side of a mountain, and whoosh, down the side of the mountain it would come. And video 2 deals a little bit more at the end with the mud flows called lahars that would come out of a mountain like Fuji. Okay, here is your classic, what we call a stratovolcano. Strato, it's made of strata, layers of stuff. You see, what can happen is, this is the Mayon volcano. It's in the Philippines. And as it erupts, hopefully, by the way, you just paused this video, looked at those clips that are on there, and then we'll pick it up again after after you've seen ash flows and lahars, mud flows and ash flows. You'll see them, and we'll go on. So stratovolcanoes, like Mayon volcano here, are made of, so as this erupts, there'll be an initial explosion or eruption, and it will shower ash and loose rock down on the volcano, and then some magma will come out of the volcano and cover that loose ash, so that you get strata or layers of loose material covered over by hard lava, and that accompanied with the steep sides of these stratovolcanoes make them much less stable than the shield volcano like we saw with Hawaii. So here's Mayon a little bit closer, very steep-sided. In fact, you may wonder, does that ever even erupt? Yes, it does. So here's some smoke coming out of the top of Mayon, but there's it actually erupting. So after it had laid down some ash and rock, it covered it with lava and made a volcano that does not have as steep a slope and does not have as stable a slope, but steeper slope, and can fall apart, like you'll see in those video clips, or you have seen hopefully in those video clips of Mount St. Helens. Okay, so obviously granitic eruptions are a bigger deal, and the structures they create, stratovolcanoes, are really epic looking. But people noticed other features. Let's go to a place in Oregon called Crater Lake. And at Crater Lake, we'll see something unique also. Here, if we look at Crater Lake, I don't want you up right now. If we look at Crater Lake, you can see there was a volcano here. There's this ridge around the side. If we zoom in on it, you can see it's not real tall, but it's significant, a few hundred feet, maybe 1,000 feet. Hold a cursor here, and down here you can see an elevation number. So if I hold it up at the ridge, it's 7,100 feet above sea level, and on the lake it's 6,100. So this is about a 1,000-foot ridge all around this particular island. And if you look at it, you can see that this is likely a volcanic remnant, especially if you look at Wizard Island here. If we zoom in on that a bit, well, sure enough, there's an old volcanic feature right there. You can see the cone in the middle. So geologists first thought that there was a volcanic eruption so severe that it blew this previous volcano right off the face of the earth virtually, and then tried to reestablish itself with this new cone. Later, researchers have looked at this and they said, well, you know, not likely. What probably happened is there was a big volcano here. There was a massive eruption. They talk about Mount Mazama here. That was believed to be the predecessor to Crater Lake. And it erupted cataclysmically. But the magma chamber that was under Crater Lake then emptied so much magma out of it that it lost its supporting pressure, and so the overlying volcano fell in on that now emptied magma chamber and made Crater Lake. This is about 2,000 feet deep. It's the deepest lake in North America, deeper than Lake Superior by almost double. It had no fish population. They put stocked fish into it now. This is an incredibly large feature. So again, if we measure it from one side to the other, we're looking at 6 miles across. And so just to give you an idea for how big of a feature that was. Nothing like the 60 miles that spans Mauna Loa, a shield volcano. So a tenth the size of that, but still a big feature. Just to show you sort of an extreme case, we'll go to the Philippines. Extreme case of a crater, caldera, I should say. And here we have the Taal volcano, and once again you can see a clear crater edge around the side, some maybe little volcanic features in there, but the unique thing about the Taal volcano is that you've got a crater, a cone and a crater that exists on an island in a cone and a crater. So it's kind of a two-step volcanic feature here. A larger caldera, a smaller caldera, and a small lake and a large lake. The scary thing about this is if I zoom out just a little bit more, oops, out, Brian, we find that just north of the Taal volcano is another very large city. This is Manila. And just to give you an idea for the distance from the Taal volcano to Manila, 25 miles. That's scary close. But the Philippines are all covered with volcanoes. Volcano, volcano, volcano. They're all over here. In fact, in 1991, after St. Helens erupted, Mount Pinatubo erupted in the Philippines. And, well, I'll tell you what, the next summer we had killing frosts in the middle of June. I don't remember getting much above 70 degrees except for a couple weeks in August. It definitely affected worldwide weather. And so these are big deals. That's a caldera. Another feature that I wanted to talk about just briefly are plutons. These are created as magma doesn't reach the surface but cools in the rock. In overlying rock. The resulting rock can be rock can contain crystals that are very large because they are well insulated and cool slowly. So pillow lavas have small to no crystals because they cool so rapidly. But plutons can have large crystals that make them up because they cool so slowly. There are some features here just to give you an idea what they look like. This is the Sierra Nevada mountains. You're looking from the east toward the west. So Los Angeles, San Francisco would be over these mountains. And this whole mountain range, the whole Sierra Nevada mountain range, is itself a batholith. So if we go to, we'll just go to Los Angeles, probably get there quicker. And if you look actually east from Los Angeles, so the opposite direction of the picture that I was showing you, you'll see the Sierra Nevadas. Oops, a little bit too far, sorry about that. So I gotta go a little north. So these are the Sierra Nevada mountains here. And interesting enough, you look close here. We think of St. Helens as the only volcano, but there are Mammoth Lakes. This is a volcanic region. If I zoom out here a little bit, we'll go up here, and there's Mount Shasta, Northern California. It's a volcano. We go up north, there's Crater Lake in Oregon. That's a volcano. The Three Sisters volcanoes, we have Mount Jefferson, we have Mount Hood up here, that's a volcano. We have Mount Adams, Mount Rainier, and Mount St. Helens right here, all volcanoes. In fact, if you look at Mount Rainier, actually I'll go back to here. Mount Rainier, it stands over Tacoma, Washington, the same way Fuji stands over Tokyo. That's also an active volcano, or a dormant volcano. So anyway, here's a batholith. So this is magma that didn't reach the Earth's surface, cooled beneath the Earth's surface, but then because of plate tectonics, was shoved up to the surface. So all this rock cooled deep beneath the surface and then was shoved up to the surface. Another feature that you might see is something called a sill. This you'd see in Glacier National Park. So here's layers of rock, and then there's this layer of cooled magma that has burned its way along those pre-existing layers of rock and cooled there. You can also see a dike. This is a layer of rock that is cooled within pre-existing layers of rock. We looked at this at the second day of class. We talked about this rock, since it's a layer of magma that is intruded into a previous existing rock, would be older than these layers of rock around it. So these are all examples of plutons, of rock that has cooled inside of previously existing rock, plutons. Okay, so right here. So we talk about volcanoes being active, dormant, or extinct, and that's good. You just don't want to just confuse an extinct one with a dormant one. We'll talk about an example when that happened. So basically, volcanoes are classified in three different ways, or two different ways. Number one is what you see there, based on its explosivity. And so you have this Hawaiian type eruption here. And that's very characteristic of a volcano like Mauna Loa. And these are typically the only ones in that system that involve basaltic magma. If Mauna Loa does erupt, it likely will erupt again. The issue is not going to be probably ash flows, definitely not going to be lahars because there's not an ice cap, but it's going to be lava flows going overland long distances, many kilometers, miles, like I say, all the way to Hilo is possible. Then number two is a strombolian type of eruption. So if we go around the world to Sicily, just off the toe of the boot of Italy, we find some volcanoes that now involve granitic magma. And in this case, just north here of Sicily, there's a volcano called Stromboli. And there are actually live cams on these if you want to go to them and talk about them while you're looking at them. This one usually isn't in effect because while it's a small eruption, they got the camera too close and it knocks it out all the time. So this one, people living right here. So these are frequent, so pressure doesn't get a chance to build up. So when this erupts, which it does frequently, I mean daily, weekly sort of thing, then it isn't a big eruption. Well, just a little bit to the south and west of Stromboli is a volcano with a clever name. It's actually a volcano called Volcano. Okay, and so, give me a second here. And so if you look at the volcano called Volcano, once again, there are people living on the island right here, but it's a little more severe than Stromboli, but not so bad that people can't live there. If we go to the island of Martinique, in the Caribbean, we're going to see the third or the fourth volcano type in that category. Now, when you think of Caribbean islands, I think you tend to more oftentimes think of a coral reef or something like that. But we need to make kind of adjust our thinking a bit. Here's the Caribbean plate. It's moving east, slamming into the North American plate. Subduction is occurring here. These are subduction zone volcanoes. These can be a big problem. And on the island of Martinique is a volcano called Mont Pelée that in, was it 1902, 1906, somewhere in there, 1904, it erupted. And so the capital city used to be here called Saint-Pierre. And this one erupted. It sent an ash flow down the side of the mountain, and it hit Saint-Pierre and wiped out the whole city. Within minutes, maybe 1 or 2 minutes, 29,000 people were killed by an ash flow from Mont Pelée. So now we're talking serious stuff. We don't want to be close to that volcano when it erupts. The biggest one here is a Plinian-style eruption, and it's named after a volcano that I'm guessing you've heard of. It's the only active volcano on the European mainland, and it's Vesuvius. Mount Vesuvius is right here. Okay, this is all Naples or suburbs of Naples. And Vesuvius erupts again. It doesn't have to go far, folks. This is city right here. It's so bad that the Italian government will pay residents that live in a danger zone, I'm not sure where that is around here, Vesuvius, $46,000 to move away and abandon their house. And not really many people have taken it. This is what Mount St. Helens looked like. When you look at that video of Mount St. Helens, think Mount Vesuvius, except Mount Vesuvius was 3 times bigger than Mount St. Helens. It was a big deal. It erupted in AD 79, but it had been active for 150 years previous to that. There were actually people cultivating grapes inside the cone. And if you look at Vesuvius, you can see its predecessor, I think it was Mount Soma, that indicates that Mount Vesuvius was active in the past and was a potential problem. And if we look at, I should just Google it. I was just going to see if I could zoom in on it. A little town called Pompeii. And I'll go, oops. I should just undo that whole thing. Yeah, there we go. And this was actually buried by ash from the Vesuvian eruption. And if we look, zoom in on Pompeii, let's see if we can find what I'm looking for in short order. There it is. You'll notice here that the houses are much smaller. This is Pompeii. This is the old city of Pompeii. And it was underneath ash, 30 feet of ash for a long time before anybody ever realized that there was a city under here. And if we go here, you can get an idea for how deep the ash is. So, here's Pompeii. Actually, I'm going to exit this a little bit and zoom out here just a minute. If it'll let me, exit ground level now. Yep. Okay, so if we hold the cursor down here, you read the elevation down here in the corner. You can see the street of Pompeii is at 77 feet. We go up here to this villa. That's 102 feet. 30 feet of ash. So this is current day. This is old Pompeii. And yeah, this was a major eruption. Some people got out, but they're not able to get away so easily. And so where are they going to run to? And so there were some people that were caught in the city of Pompeii, and their remains have been left. And let's see if I can actually do this. And you can look right down the streets of Pompeii through old archways, and you can see Vesuvius behind it here. And this was all buried. And so some people then, over 1,500 years later, noticed cavities in the ash layer. And when they filled them with plaster, they found some. Oops, I guess I need to go here. They found something kind of grim. If you look at the Pompeii victims, this is what they found. Look at this person. The detail is sometimes not good, but sometimes it's very good. You can see even expressions on faces. These are people that died in that eruption. Okay. So lastly, and I know this video is going long, I apologize for that. We have the volcanic explosivity index, because sometimes you got eruptions that are just way bigger than that previous scale can account for. And so if we consider Mount St. Helens as having erupted about 1 cubic kilometer of Earth's surface, we're going to look at some other historic eruptions that have involved significantly larger amounts of Earth's surface. It looks like this isn't going to actually open on me now. So if we go back here, we want to go to a place, it's really starting to, I've probably got too much stuff open here, so we'll see. No, that's okay. We're going to go to a place called Krakatoa. Now Anak Krakatau, and this is in Indonesia. And if you're looking at a place that you need to keep your eye on, it's Indonesia. All up and down Indonesia, which is really a string of islands, are volcanoes. All these dots here, all are volcanoes. And some of them have historically erupted in cataclysmic ways. Volcano, 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 all up and down. These are volcanoes. We're going to look at Krakatoa right here. And this is Jakarta, just a little ways away. And this one erupted in 1883 in cataclysmic fashion. It may be the one exception to where a volcano did erupt so cataclysmically that it blew the entire volcano off the surface of the Earth. This is all that's left. It erupted probably over several months' time. There was a precursor eruption that got the one witness, a British sailing vessel called the Sir Charles Ball, I think it is, B-A-A-L, away, and then this thing erupted. And it erupted so cataclysmically that it sent a sound wave that traveled across the Indian Ocean, and it has been verified that it actually hit the coast of Africa 4,000 miles away about 4 to 5 hours later. If you can imagine a sound so loud that it could travel across an entire ocean basin, that's what likely happened. This was 25 times the size of Mount St. Helens, and it's believed that a possibility is that the ocean floor actually popped open because as the magma chamber filled up and swelled up, it may have cracked the ocean floor open. All that ocean water may have flowed into the magma chamber. Remember, water is one of the volatiles, and it just exploded in response to that. It's said that one survivor said it created such a hole in the ocean after the eruption that it took 30 minutes for ocean water to fill back in and fill that hole up. That's an incredible hole, if you think about it. So that's a big deal. If you go down the Indonesian archipelago just a little ways to an island called Tambora, oops, I need to go back. So we'll find an even bigger volcanic eruption. This was 1815. Tambora erupted, and we're talking about 125 times the size of Mount St. Helens, or 3 times the size of Krakatoa. So here's Tambora, and it erupted so large that the ash and sulfur that it kicked out of there circled the Earth, and it affected Earth's weather to the point that there actually were significant snowfalls and frosts every month of the year in New England, destroyed agriculture around the world. And they called 1816 the year without a summer. The biggest volcano that we know of, the supervolcanoes, I'm guessing some of you have been there, would include Yellowstone National Park, where you have a volcanic eruption that is on the neighborhood of 2,500 times the size of Mount St. Helens. If this went up again, if Yellowstone went up again, it would likely create a volcanic winter that would really have strong negative impacts on the human population. So 2,500 times is Yellowstone. There's a volcano in Colorado called Galeras Volcano. Not Galeras. Now I'm forgetting the name of it. Darn. It's by Creed anyway. That was twice the size of Yellowstone. And so these are the big ones that we don't want to have go off. Okay. I apologize, that's about twice too long what it should be. I'll see you in class on Tuesday.